Okay, so I've got a turbine here that has one inlet, two outlets with the properties shown. I got some pressure, temperature data, saturation over here. Okay, and notice that the outlet of 2 is 20% of what's coming in at 1. Okay, I also have power created of 6.8 times 10 to the 6 BTUs per hour, and I'm losing heat at 5 times 10 to the 4th BTUs per hour. As per usual, we're going to neglect kinetic and potential energy, and I want to find the mass flow rate of the steam entering the turbine. So the first thing I need to do in this problem is I need to calculate my H values. So I'm going to go look up H1, H2, and H3 from my systems here. And I've got basically two properties, so I should be able to find any other one. Okay, so I'm going to start. This is water. Steam, yep. This is water at 1800 psi and 1100 Fahrenheit. So at 1800 psi, oops, we would be over here, go to 1800. So in this table, this is table A4E, 1800 and 1100. Okay, my H value is 1542.5. Okay. State 2, I have a pressure of 600 and a temperature of 500. So I'll go to 600 right here, and 500 is right here, and my H value is 1216.2. State 3 is saturated vapor at 1 psi. So I come over here to state, I come to my pressure table, 1 psi, saturated vapor enthalpy is 1105.8. So I have all of those. I've set my states. I found the enthalpy for each state. So again, this was 1542.5. H2 was 1216.2. State 3 was 1105.8. And these are all BTUs per pound. Okay, so that's the first step of the problem. So now I know all of my H values for each of the states. The next thing I need to do is develop this conservation of mass principle, which basically states that the inlet mass equals the outlet mass for steady state. So that means m.1 equals m.2 plus m.3, right? Where m.2 is 0.2 m.1 plus m.3. From that, I learned that m.3 has to equal 0.8 times m.1. So I don't know the mass flow, but I've got them all related to the incoming mass flow, right? 20% goes this way, 80% of it goes that way. That's essentially what we've got here. And again, that's because the mass flow in has to equal the mass flow out. Okay, so now we move to our first law equation, right? For steady state, the change in energy is 0. I have no potential or kinetic energy effects, so all I really have is Q dot minus W dot plus mass flow in, H in, minus mass flow out, exit, times H exit, right? So again, it's heat minus work plus basically the enthalpy in minus the enthalpy out. And I know everything in this equation, which is to say Q is Q is 5 times 10 to the 4th. That would be BTUs per hour. So I divide that by 3600 to get everything in seconds. So that's Q minus the work, which is going to be 6.8 times 10 to the 6th divided by 3600, plus the mass flow in, which is M1 times H1, which is 1542.5, minus the mass flow out, which is, I've got two of them. I got 0.2 mass flow 1. That is for H2, so that'll be 1216.2 minus 0.8 mass flow 1 times, again, that's how much is flowing out at state 3, which is 1105.8. So I've got a big equation. Everything's in BTUs, pounds, and seconds, right? So Q minus W, enthalpy in minus enthalpy out. The only unknown in this equation is the mass flow coming in, m dot 1. And through the magic of algebra, I find that the mass flow in is 4.59 pounds per second. So again, on the problem like this, first thing you do is you set your states. For this case, that is find your H values. Once you find your H values, deal with your masses. My mass flow in equals my mass flow out. So I get everything in terms of the mass flow in. Then I use the energy balance, knowing Q and W, knowing my enthalpies, I can now calculate what that mass flow actually is.